So I'd like to welcome everyone to the 964th monthly meeting of ATMoB. It's June 8th, and this will be our annual business meeting, so we'll have committee reports as well. And our guest speaker will be a postdoctoral here at the CFA, Morgan MacLeod, on a very, very interesting topic about potentially a star swallowing its planets.
Not our planet, though, right?
I don't think so. It's pretty orange out there.
That's why the skies are orange.
So the agenda is going to be a big one, so try and get to it. I've got everything underlined that is sort of atypical to a normal meeting. So we'll have a board election and a lot of the annual reports for the various committees, and we'll vote whether to hold the bonus July meeting. So with that, we'll get right to it.
So this is Glenn.
Awesome. Always. The security camera, Bigfoot, or UFO.
Where do you want to stand?
That chart.
I'll stand here.
Oh, I'll stand over here then.
We'll see how the slides are going. Okay. Now, what do I hit here?
That's the
This one.
left arrow.
Okay, nothing got ejected. All right.
No smoke.
I will love the light for it shows me the way, yet I'll love the darkness because it shows me the stars. By a man named Og Mandino, who's an American author. I guess he graduated from Natick High School. And I looked at his bio, but this was a day ago, so I've already forgotten what it was on there. But I think he was an individual who did a lot about self-help and just self-confidence. I think he had some issues himself. He almost committed suicide at one point. So Bruce is nodding his head. Do you know more about this individual? Or?
It was a motivational speaker.
That's it, okay.
Yeah.
All right, we had a supernova in the galaxy M101, and I'm not, Richard arranged these slides. This is an AAVSO chart showing the location of the supernova with some of the comparison stars.
This was from an article by Bob King on Sky and Telescope's website. And Bob was nice enough to kind of sketch in where the galaxy's actually located here. And I thought that was a really cool thing to see, because if you're going to look at this visually, I think the challenge is finding the galaxy itself. It's actually a fairly faint deep sky object, very challenging. So if you can't see much of the galaxy, it's hard to know where to look for the star. So I was very appreciative that Bob took the time to put that in.
And I did make a visual observation myself with a 10-inch scope, and again with the smoke, moon, clouds, the whole thing. All I saw with a 10-inch scope was just the nucleus of the galaxy here, and then the supernova itself. And I'm not sure how these slides came out in the arrangement. Let's see what we got. Okay, I got a call from Sal Risha, and some of you have been seeing some notes on the internet. And I did a lot of research, bouncing back and forth. So my brain was so scrambled for this. I had to write down exactly what happened here, so bear with me, because I don't usually like to read things. But I made a note. Sal recently asked me to confirm that an image he took of the galaxy M101 on the evening of May 18th might have captured the supernova SN 2023 IXF prior to the announcement of discovery. And that's Sal's image right here with a couple of magnitudes of field stars. And he's showing the galaxy right there. And again, I said I would do this instead for the people that are watching at home. Let's see.
So there's a blown up.
Oh, wow. What did I hit? Look at that. I destroyed everything.
We shouldn't let Glenn touch buttons.
So we have a zoomed in version here.
Okay.
To push buttons.
Maybe a little more apparent.
All right, I'll just back up to the previous one and just see what we got here.
See that greenish star? That's why I thought he discovered it, did a pre-discovery.
Yeah, you can
Wait a minute.
just light touch, very light touch.
See that
So
star
this
there?
is it right here.
Projector.
That's why I thought Sal had a pre-discovery image. But when I superimposed images over the actual supernova, it was just offset by a little bit. Plus, that star shows up in multiple images going back years. So that's not the supernova.
All right, here's the
Sorry,
thing. All right, I want to show these two field stars, and bear with me because I have not tried this, but there's what Sal's image is. That's field star. There's a star in the field of view, and there's a supernova. You look at the angle. Just go to that, and I'll point up here. Yeah, I'm going to just. I love
Here,
technology.
switch with me.
Yeah. Okay. All right. This is Sal's image blown up. And again, this was taken with a 6-inch scope, I believe,
6-inch
and
scope,
light polluted sky, so it's not gonna be the same detail as this, but there's one field star, another field star, there's a supernova, and there they are here, here, and there. And one of the things I noticed, there was a kind of a field star above that. Now, I don't have that with me, but I went through a whole bunch of AAVSO charts, and the first thing, I'll go back to my script if you'll bear with me here. I began by determining the magnitude of the supernova around the time Sal took its image. First of all, was it visible at the time he took the image? And he took his image on, I think it was 9 o'clock on the 18th, 9:30, which translates to May 19th, Universal Time, May 19th, 0.0625. That's when Sal took his image. The AAVSO, in their announcement, just reported a pre-discovery image and had a magnitude of 17.3, and that was made a little bit earlier, a little bit before. So I would say at the time that Sal took his image, that supernova was already at least around 17th magnitude. The next thing was determining what was the faintest thing that was visible on his image. And again, it's kind of tough because you have pixels and you have very faint stars. So what I did, this is the F chart. This is an F chart scale from the AAVSO's variable star plotter. There's the location of the supernova. And the faintest field star they identified was one that was 16.2 magnitude. There was also a 14th magnitude star here. The faintest star showing, this scale, the F scale goes down to 18.5 magnitude. Now again, I don't know how well things translate with his, but here's a 14th magnitude field star, there's a 16th, and here is, let's see if I got these pegged right, 1, 2, 3, and 4, and there's a supernova. And I, yeah, 1, 2, 3, 1, 2, 3, and there's a 4th star somewhere, yeah, right here. Supernova's right there. But I'll just look at these. 1, 2, 3, Sal's image. 1, 2, 3, that's where Sal's image is. Now I went to the G chart just to see what was faint, and there was a star just above Sal's image that would have been around 20th magnitude. It just wouldn't show in Sal's picture. So I am 99% certain that Sal did in fact catch the supernova. It matches perfectly with the AAVSO finder chart and the fact that there's nothing much brighter than, say, 20th magnitude in that immediate vicinity. The 1% I'm not sure about is I'm not an astro imager. I don't know if there could have been an artifact.
Yeah.
So
I thought he did it first. What I did is I superimposed his on prior images, and it's just offset a little bit. So the supernova, if you look where those lines are, is slightly to the right.
okay, but nothing
By the
shows.
way, those lines aren't precise. That was just a visual estimate.
Okay.
And so
But
I'm
that's
not
not, but that's
I'm not
not
going to claim any
pre-existing.
accuracy with those.
No, I know we get a whole debate here. I was going to bring a suit of armor.
Well, what did Dan Green say?
Dan Green was confused. That's why I sent him a note as well. He wasn't sure.
Dan Green did not have an interactive conversation with me, except to say, send me what your observation was.
Okay.
Initially, when they reported it, Dan Green is the head of the Central Bureau of Astronomical Telegrams. It's where things are reported in the world. Brian Marston used to run that agency years ago. And I try to get a phone conversation with him, but I haven't been successful.
I'm just looking at the plotting again. 1, 2, this field star, the supernova. We're also looking at a couple of stars out here. You look at the angle, and here they are, here, here, and there. Now the angle is very similar. So again, I would say 99%. The only thing that makes me any doubt, again, is that I don't know much about astroimaging, if that could have been an artifact. But again, you look at the stars here. We go backwards, go back slide.
And also, just as an FYI, when I do imaging for deep sky, what I do is I save the image after so many exposures. So in this particular case, I have 10 separate stacked images where, say, number 2 has all of what 1 has plus 2. The third one has 1, 2, and 3, and I have those over 20 minutes. So I have multiple images. None of these are processed. They're just a raw image that comes from SharpCap Pro. So,
Probably move forward then.
and I thought the quality of these things was awful, by the way. they were just filled with noise, because I don't do,
Go
I
back one
would
more
look
time.
for
So we want to get the
astrometrics.
meeting going here, sure.
I think we ought to rename it on the,
Just going back again though, this is the AAVSO chart to magnitude 18.5, and there's nothing in this area. And I'll point out these 3 stars again, they go toward that one. And here are those 3 stars, and there's Sal's image right there. So there is something there on his image that's not there on the AAVSO chart.
and it's on multiple images.
And if you look at this, again, these are those stars you just saw, the 3 stars in that EF chart.
Could potentially be this faint one here.
And then that green thing right there. And actually, I think those do line up pretty well. 1, 2, 3, 4. 1, 2, 3, 4. So like I say, 99%, I'm pretty sure. Now, the only other thing is how scientifically valuable is this? Well, you can't, I don't think you can get to the nearest tenth of a magnitude with what's here. But considering that was with an 8 or 3, a 6-inch scope rather from light polluted skies, it's a pretty good job.
The way to do it is to blink.
Yeah.
And that's, I just put it on top, and there was a slight offset. But I'm happy to check it again.
Yeah, the other thing is, there's nothing, the AVSO chart, there's nothing in there right down to 20th magnitude. I don't get those deep as I could.
Okay.
So
So
there's a.
that's
faint
gotta
one
be
up here.
something. It could have been one of Rich's geocentric satellites, right?
Yeah. I think we should move
Wrong
forward
part of
though.
the sky,
Get
but
a
that's
long
okay.
meeting.
So it's
Okay,
okay.
well, we will continue.
It's not
Again,
my satellites.
thank you, Sal. Okay, we'll continue. All right, here are some of the club members' images. Here's Mario's right here, there's a supernova right there, nice image right there. And we'll continue. Richard, go ahead and talk, because you put these slides together
Just
for
as
us.
a warning, if you're gonna try to estimate magnitudes, you can't do it from color images. You gotta take one of your
Yeah.
raw images, preferably a black and white in the visual, so green image filter is the best way to do it.
You know, for visual observers, again, this galaxy is actually really difficult. And with most backyard telescopes, visually, all you're going to see is this nucleus here, right here.
Right.
And so the way I would, if you want to still go out and look at this, and it's still easily within the reach of 8-inch telescopes and above, is to use the geometry of this 12.9th magnitude star here, the nucleus, and then this. This is closer than it looks. And so, you know, be patient if you go out to look for it. You won't see the spiral arms of the galaxy, but you might see the nucleus. So using that 12.9th magnitude star and the nucleus, you can, you sort of, you know, you'll see the angle works for you that way. The smaller the telescope, you can probably see the supernova in a, you know, it's 11th magnitude, so a 3-4-inch telescope, you'll see no hint of the galaxy. So it's hard to pick out the right star in a star-sprinkled field of view. But just keep that in mind. But so go ahead, so we get some great shots from folks.
So I'm a newbie at this, and I think the biggest thrill is to just watch the image accumulate on my laptop. Because when I look through my telescope and I look at the laptop, I see nothing. Nothing. Just a few stars in the field that I can focus on, and then I have to wait for the thing to accumulate. And it's a real hoot just to watch it. I mean, it's amazing.
I'm amazed you can do anything from some of them.
Hey, me too. I thought it was just gonna be solar system objects.
This actually isn't a star right here, this is an NGC, it's an H2 region.
Yeah.
In M101, so it looks star-like in a telescope, but it's actually.
Yeah, if you go back to my image, I did it in H alpha, and you can see it's red.
Yeah, here it is, right here. So
That's
this
all
looks
H.
stellar in a backyard telescope, but
Right.
it's not. So there's that one.
Nasmus?
Nasman has a
Pre-
pre-image from
after.
March, and then the supernova, you can look for the geometry here to find the supernova with your backyard telescope.
Just running north is that way in that image.
Okay. And here's some
North is
shots
up
by
and
Doug
down.
Palm. There you go. So
The
this
one
is-
of the supernova there was shot through through smoke. It was
Yeah.
Smoke's
so
terrible.
dark that I could only see about 3 stars with the naked eye.
I believe it.
I'm surprised that I was able to shoot anything.
So this is today's AAVSO light curve for visual estimates. Are still putting the supernova between 11 and 11 and a half magnitudes.
Yeah, I made 2 visual observations. They're messed in here someplace, but I had it both times at about 10.8. You can see it's just slowly dropped. I'd say if you look at all these averages, it's probably a little bit below 11th magnitude. Now, there was a supernova there about 10 years ago that reached 9.9. This was a type 2 supernova, so it was a supergiant star that collapsed, and there's the result. And I just want to say one thing. Since I made a visual observation, I wasn't going to try to make a sketch because there's just too many stars in the field of view. But the thing that kind of excited, this is a star, that galaxy's 21 million light years away. So this star blew up 21 million years ago. And those photons striking my retina and sending whatever electrochemical message to my brain was triggered by that star that blew up 21 million years. Just the photons, to think about that, photons that are actually causing some type of a chemical reaction in your brain. That just found that amazing. Even though the object itself wasn't an exciting thing, it was about 11th magnitude star.
Don't you feel guilty now that you got in the way of them?
Those little beams went for 21 million years. They wanted to hit the ground. They hit my eye instead. Yeah, sorry about that, photons.
Go ahead, Ryan.
Yeah, just the previous supernova was 2013, I believe, because I caught that one.
Yeah.
2011.
Okay. And notice the curve on this. This is what the value is of taking repeated measurements. It's a slow diminish, as you say, and that means it's not a type 1A. Type 1A kind of spikes and comes down rather rapidly.
Yeah.
This one is slowly coming down, which tells you it's definitely not a type 1A.
21
Because
million
it turns out
years
it's a
ago.
type 2.
And that's why I included the slide, to encourage people to go out and look at it. You know, a few weeks after the event is discovered, you'd think, well, I'll not see anything, but you will. This is still well within the reach of backyard telescopes. So I encourage you to go out and, first of all, find M101.
Yeah, if this was a type 1A, it would already be down past 13.
Yeah, so this one's still quite visible. So get out there and look at that. Okay, next slide, next slide. Just one slide, Ellen, just do one slide.
Go ahead.
So there aren't many observing highlights for June through July. Venus reached greatest elongation east on June 4th. The moon is near Venus the 21st and 22nd. Mars and Venus are close to each other in late June. Here's the clubhouse Friday, Saturday observing schedule. If you're interested, it's like Steve reported, it's in the newsletter. Weather permitting, of course, but we've got a pretty good system now in place where I send out reminders the Sunday before. Eileen you got yours a week early because I hit the wrong button.
It's going to be clear then.
I hope so. But we have a pretty good system in place, so on those weekends, we encourage everybody to come out to the clubhouse and observe either with your own telescope or one inside from inside the clubhouse, or come up to one of the observatories and look through some of the scopes up there. So the next slide, please, is the planet roundup. Saturn's actually coming up earlier now, 11:45 in the morning. It's in western Capricornus. The ring tilt this year is 8 to 10 degrees. So those rings are starting to get kind of, hard to see. The Cassini division will be a challenge this summer because the rings are getting pretty edge on. There's a ring plane passage in 2025 early, but that's near the sun. But in the December of 2025, there's a nice ring plane passage that we'll be able to observe in the dark sky. So that'll be kind of fun to watch. Jupiter comes up at about 2 in the morning. Did anybody besides me catch the occultation the other day? The daylight occultation? It was awesome. It's rising at 2 o'clock in the morning. It's high in the east just before sunrise. Venus, 43 degrees east of the sun, minus 4.4 magnitude, 36% illuminated. Remember, it's supposed to say late June. Transit's about 4 in the afternoon. Now is the time to start honing your skills as a daytime observer. Get out there and look at Venus. It's 40 degrees away from the sun. You'd have to want to hit the sun on purpose when it's that far away. And the reason I'm encouraging you to do so, I popped a couple of slides out because I knew this meeting was going to go long. But in July, I'm going to really encourage you to start looking at Venus in the daytime, practicing for the next inferior conjunction. That happens on August 12th. I love. No. My record is 1.69 degrees away from the solar limb without a filtered telescope. I can see both. Without a filter on a telescope, you have to be extraordinarily careful when you're that close to the sun. But in August, am I too close? Oh, sorry. In August, Venus will be over 7 degrees south of the sun. So it's a perfect year to look at Venus as a razor-thin crescent almost an arc minute across. So start practicing now for that, all right? And so that's your homework. Go ahead, next slide. And here's the
Observer's
observer's
challenge for
challenge.
June. Yeah, this is a fun pair.
an awesome
5774/5. Well, I'm saying fun because I want to encourage people to look for it. It's a pain in the ass.
Watch
Pardon
the
the-
piece of paper.
The galaxies, it's a pair of galaxies. We'll go to the next slide. I think we got some club members have taken some pictures. Mario Amato's image over there. We have Doug Paul's right here. It's a pair of galaxies. 5774 is a face-on spiral, and it's a fainter of the two. 5775 is the lengthwise one. That's another spiral galaxy. It's edge-on. And that was the brighter of the two. That was discovered by William Herschel. Now, here's where I have a problem. The magnitude is listed as 11.4. Yet Herschel, when he cataloged this, he cataloged it as a class 3 object. Class 3 were faint nebulae. And usually an 11.5 magnitude galaxy is not a faint object. So I'm not sure. And the other one was even fainter. In fact, Herschel missed that other one. And it wasn't discovered until about 70 years later by that great telescope in Ireland, the Lloyd Ross telescope. I think it was a 62 or 72 inch reflecting telescope. So that fainter one, now again, our optics are much better nowadays, so you should be able to pick both of them up with a 10-inch scope if you have dark skies. And I know, Rich, you tried, even with the 25-inch, it was hard. You probably saw the brighter one of the two, right?
I could see the edge on spiral, but this 5774 up here was completely invisible.
Yeah.
It just, I couldn't see it. And I tried and tried and tried.
What you don't see, what you can see in here, somehow the projector, there's actually a connecting gas bar between the small galaxy and the end of the large galaxy.
Yeah, this is an arc pair, yep.
And that's one of the challenges, by the way, is if you can see that arc that goes between the two. No, I'm talking for visual, visual, or the imagers, it's a challenge for imagers. Okay, I should have mentioned
Yeah,
that.
I didn't look for it, but this is IC 1070. That might be even easier than 5774.
But again, we've had problems. The smoke, I'm just not even trying these. Now, the thing is,
It was smoky the night Herschel looked at the other one and gave it a 3.
oh, that was right. There was a forest fire in Scotland. That was what the problem
So
was.
it's an interactive.
But again, this is a class 3 Herschel object, and he didn't even see this one. Okay, we'll continue. I think we have some more images. Mark Helton over there, Chris Elledge with Middleman again. This, again, you look at what we've got right at our own disposal of our club. That's amazing stuff. So I thank all of the people who took those images. And I think the next one's a preview for next month. NGC 6217, it's a barred spiral galaxy, not far from the bowl of the Little Dipper. There's the bowl of the Little Dipper, so it's not that far. I forget which star that is in the Little Dipper. It's listed as magnitude 11.2, so it's a little bit brighter, at least in the textbooks. But the thing is, I did check Herschel on this one, and this was a class 1 Herschel object, so Herschel considered it bright. The other one he considered faint, and there was only 0.2 magnitude difference. So this one, I think we got a chance at if the smoke again clears out of the way.
Brian, it's pretty easy to find, actually. Like Glenn said, here's the bowl of the Little Dipper right here. And so I keyed off of these two stars and managed to star my way over to here. It's a fairly easy object to see. It's actually pretty okay. Easy to find, relatively easy to see. I think the next slide has statistics in all these galaxies. And I showed you the first 2 slides last month. The stars come from Keppel and Sauner's book. And they give 6217 3 stars. Magnitude 11.2 with a surface brightness of 13.2.
Look at the magnitudes by the way, but this makes more sense to me. 12.2 and 12.5. I think those are right. Yet most of my resources had about 11.4 for the brighter.
But look at the surface brightness. This 12.6 was a bit of a challenge. And the one I couldn't see is the surface brightness of 14.3. That's a faint. For light polluted skies, that's a really faint object. That's why the July object's a little bit more optimistic here, with a surface brightness of around 13.2. So despite the fact that they are challenges, we certainly encourage you to go out and observe them, whether you're doing it visually or whether you're taking images. It's always good to challenge yourself either way. And so, please try to get out there, and if you really feel like writing it up, send it to Roger Ivister, and he'll put it in his Observer's Challenge report. And I think that's it. I think that's our last slide, except for the committee report.
Okay, I'll let you take that.
So I'll do this fast. I'll do this really fast. Because I've got way more to talk about come the outreach. So Glenn Chaplin, I continue to present the observing report at the monthly meeting. I continue to offer via email the monthly 19+ objects to observe. I was going to stop that, but I got some feedback from folks asking me to keep going with it, so easy peasy. That includes the mini Messier marathon and the circumstances of Jupiter's great red spot and shadow transits when the planet was visible during the evening hours. At the January 2023 monthly meeting, I announced that asteroid 11831, 1984 SF3 had been given the official designation of 11831 Chapel, honoring Glenn Chapel's contributions to the AAVSO database and his 20-year career as contributor to Astronomy magazine. Respectfully submitted.
So with that, I'll introduce our speaker, who's actually a postdoctoral fellow here at the CFA, Morgan MacLeod. And his talk will be about the star swallowing its planet. So as stars evolve and expand to become giants, they can swallow their close-in planets. Morgan MacLeod will share observations reported in Nature on May 3rd that may show the outburst caused by one such planet being engulfed by its host star. Morgan will talk about how the source was discovered and share what he believes this means for understanding how stars coexist with their planetary systems. Morgan MacLeod, is an astrophysicist and postdoctoral fellow at the Center for Astrophysics here. And he's most interested in the brief transformative moments in stellar lifetimes when the stars directly interact. I may have accidentally clicked some stuff, but I assume with their planetary disks or with each other, there's a multi-system. Sorry for the clip here. So let's see. So you're welcome to come up.
Joining the Zoom as we speak. Sorry.
Thank you.
It's great to be here. Thank you all.
Thank you for speaking with us.
Okay, so do I not join the computer audio or do
You
I?
can. We'll have you mute the microphone and the speakers. And then the system.
Alright, there you are. I will make you a co-host.
So you should be able to share. And then we'll just switch straight to
Just share my screen.
Okay. And then you can present as if you were presenting. Yeah, and both the people at home will see and we'll see that idea on the screen.
It says this will stop the other share screen.
Go ahead.
That's okay. Continue. Okay. Great. Play. And just minimize that. How's that look? Looks good.
All right, great.
Awesome.
Well, thank you all. It's a pleasure to be here. This was a good impulse for me to come out. Corey had emailed someone at the CFA about volunteers and they sent it along and I was like, oh, I need to come because I actually joined in 2020. And so I've been a member since then, but and I've been on the email list and stuff, but I haven't come out in person. So it's great to be here. And I want to tell you about a really fun project I had the chance to work on where we think we detected that outburst that followed a star swallowing its planet. And so I want to tell you a little bit about how that work happened and also tell you about kind of the case for why we think that interpretation might be what's going on. Okay, so this story starts with the Palomar Observatory and the especially the Zwicky Transient Facility there. And so that's I've always thought of it's sort of a funny name. It's like a factory for astronomical transients, but basically these are wide field telescopes that are surveying the sky and looking for things that change. But a really critical clue was also NASA's WISE infrared space telescope. So this has bands at 4-ish microns, so much longer wavelength than visible. And in the background, this is the Milky Way in infrared light. And I think it's kind of amazing that everywhere that we see dark bands in our night sky is glowing brightest in dust, cool emission. So this is, you know, a few hundred Kelvin glowing bands. Okay, but the transient night sky isn't new. This is the report from Song Dynasty, China, of supernova 1054, which of course is the middle of the Crab Nebula that we know now. Here's a map from Tycho Brahe talking about a stellar nova in 1572. This nova, the Tycho's supernova is actually in some of the online supernova catalogs. And one of the things that I find great about this is that it's shortened to January of 73, but really it's 1573. So maybe they should have put a few more date entries there. But what's remarkable about these objects, right, is that they brighten really quickly. In general, things tend to brighten pretty quickly and then take a long time to fade away. And you know, here we're fading away over almost 10 magnitudes between peak there and minimum. So you can see the faintest apparent magnitude is about 6, because these are all naked eye observations in a much darker night sky than we have the privilege of ever seeing. But a critical part of the sort of digitization of this process of finding things that change in brightness in the night sky has been cameras, actually. So, and something that I found interesting about it is that new cameras have been really involved in revitalizing kind of old telescopes in a lot of cases. And so what people are doing is, this top image is the Zwicky Transient Facility Telescope. It's on the 48-inch on Palomar Mountain. And just look at this big camera. I mean, it's like half as big as the back of the telescope. But what folks are doing is building mosaics where they tile different, a whole array of CCD chips. And so the goal is to make a camera that is actually big in the sense of megapixels or something, but also physically big, because the more of the sort of image that you're receiving at the back of the telescope, the broader field of view these systems can cover. And that's, if you're looking for rare events, that's really what matters, is the combination of depth, the sort of faintness to which you see, and the area that you cover. That kind of defines a volume of space that you're surveying. So we've already seen this image tonight from Mario, but we've got the supernova here. And so I just wanted to say that, you know, this is very much sort of part of the story of understanding the time variable night sky. I have a colleague, Carolyn Wong, who's here. And as you were mentioning, supernova 2011 FE went off in M101 also. And so there's a lot of HST imaging of this galaxy. And in those HST images, you can actually see Mira variable stars. And so what she's doing is looking at their light curves to determine their periods, and using that along with 2011 FE to calibrate the luminosity, period luminosity scale, and essentially form that connecting rung in the distance ladder between variable stars and supernovae. Okay, I like this plot because sort of everything is on it, but it takes a little walking through. So the x-axis here is time, so like a characteristic time scale for different events. And then the y-axis is how bright they get in absolute magnitude. And so down at the bottom are classical novae. These are sort of tens of days, and they fade away over hundreds. And they're, in sort of the grand scheme of things, relatively dim. Up at the top are the most luminous supernovae we've ever observed. They take they rise and fall over hundreds of days. There may be magnitude -22 at peak in V band. And so the absolute magnitude is the magnitude if it were at 10 parsecs. Then in between we have everything else. So here's the core collapse supernovae, like the recent event in M101. There's type 1a thermonuclear supernovae, like the 2011 event in M101. And the more we look, the more we're finding things in between these sort of broad categories that we knew from the start. And so this is a plot from 2011, but in the in-between, we've been finding more and more things. And so there's this class of objects sort of between novae and supernovae that have ended up being called luminous red novae. Luminous was because they were more bright than classical novae. And the red was because they have redder colors than classical novae. And in particular, classical novae tend to stay quite blue through their whole evolution. And these get redder and redder with time. What that represents is the fact that gas is just cooling off. And so the source itself is becoming cooler as time goes on. So we're going to talk more about those objects in particular. And one of them, and this is a particularly remarkable source that was identified in the Zwicky transient facility data. This is the visible band data. And I've centered it on days from the peak. But in the back here, you're seeing the infrared data. And so this is from the WISE Space Telescope. And actually, so this source brightened in May 2020. But it didn't really stand out actually from everything else that was out there. And so it turns out that the challenge is not so much finding things that vary in the night sky, it's actually sorting them all out and trying to figure out which ones are most interesting and that you most want to follow up. And this sort of rise over about a factor of 10 to 100 and then sort of beginning of a slow decline looked a lot like the sorts of flares that young stars tend to exhibit. And there just weren't like resources to follow it up at the time. But we came back a couple of years later and my colleague Kishale, who is at MIT now, was doing some work taking the decade of WISE data and looking for things that change in time in that data. And so WISE observes the whole sky, but it does so about once every 6 months. And so that means you have, for each star, something like one data point every 6 months. That's what's in the background here. And we realized that this source was incredibly bright in the infrared, at the same time as it's fading away in visible light. And that looks a lot like these luminous red novae class of sources that I'll come back to what they are. About a decade beforehand, so this is an image from 2008 and 2009 where you can see the little arrows marking the location of the source. This is a faint star. It's in our galaxy, but we don't know how far away it is. All we have is it's basically H and K colors, so near infrared colors. And it's almost completely invisible in most archival like V-band imaging because it's so dust obscured. So this is right along the plane of our galaxy, and it's behind about 3.5 magnitudes of dust, we think. So by looking at the observed H minus K color, and then asking what column of dust would it be behind, we can ask how much redder than a normal sort of stellar color does it look. We can use that to estimate the distance. And so you get a combination of a distance estimate and an amount of dust that it's sitting behind. And so in the end, we think it's something like the sun sitting behind about 3.5 magnitudes of dust. So it appears 3.5 magnitudes fainter than it truly is. And it's possibly somewhere between 1 and 4 solar radii. And so it might be either on the main sequence or just starting to evolve. Okay, but why is this a star engulfing its planet? And I think to talk about that, we have to step back a little bit. One aspect of this is it shows all the really distinctive features of pairs of stars merging. And that's that class of sources that ended up being called luminous red novae. And we only later figured out were stellar mergers. But when two stars merge, what we tend to see is that there's always a sort of simmering precursor brightening that happens over a pretty long time. So no, ballot. No, it's great. So there's a slow brightening, and then a bright flare, and eventually a fade away. So the precursor brightening happens over sort of many orbital periods of a binary system. Eventually a pair merges together and causes the transients that we see. So this source is brightening by about 4 magnitudes and then starting to fade away. And something you see in this plot, for example, is the bluer colors fade faster than the redder colors. And that's showing you that the source is getting redder as a function of time. Eventually, some material has been expelled from these merging stars, and it cools off, it forms molecules, and then it forms dust, and we see them fading away in the optical, obscured by their sort of dusty surroundings, but really bright in the infrared. And the source that I just showed you is similar to this kind of sequence of events, but it's scaled way down. And in fact, it's scaled down by a factor of about 1,000 in brightness, in expelled mass, and everything. The reason stars might swallow their planets in the first place has to do with their evolution. So as stars go along, they're fusing hydrogen to helium in their cores. We know that. But then as those cores become more compact, the burning, the sort of thermostat that regulates a main sequence star, the pressure from that hot central burning region, kind of fails. And the core contracts, and there's really vigorous burning in a shell around the helium core. And that makes the outer layers puff way up. And so the sun will extend to about an AU in size. And right away, you know that means that Mercury is in trouble, Venus is in trouble, and we probably are too. I think the consolation prize, if you want, is that, as you know, the sun along the main sequence is slowly getting more and more luminous. And so that means our equilibrium temperature as a planet is slowly rising also. And so I think the estimates are that in about 1 billion years, we will have boiled off all the liquid water on the planet. And so that deadline comes a little sooner than the 5 billion years that we end up swallowed. But either one, I think, is long enough that I'm not worrying about it. This is just a scatter plot of separation of the catalog of known exoplanets and the planet radius. And so down at the bottom, you have sort of Earth-like things. Up at the top, you have Jupiters. In the middle, you have Neptune-ish size things. And this is, 1 solar radius, 10 solar radius, 100 solar radii. And so as those stars evolve, a main sequence star is 1-ish solar radii. The sun will then get bigger and bigger, 10, and out to 1 or 200 solar radii. And so that means that of the sort of few thousand exoplanets that we know, almost all of those, as their host stars evolve, will end up swallowed at some point. And I suspect this is something that you all were thinking about or cognizant about. I was talking to one of my friends who was a middle school teacher for a long time, and he tells stories about talking about the fact that the sun will eventually swallow the inner planets with his students. And he had a great exercise where they talked about how big is 5 billion. And so he had them stack pieces of paper and measure how high they were. So like 300 sheets of paper is, a stack like this, and how tall would it have to be 5 billion? It's really big. And so this is a process that I think we've been cognizant of for a long time, but we've never caught happening. And I think there's something amazing about the fact that stars and their sort of co-inhabitants, these planets, exist kind of stably for billions of years, and then all of a sudden, at some point, a planet like Mercury or Venus or Earth ends up swallowed by that star. Okay. There's two things that happen when a planet plunges into a star. The first is that the act of kind of splashing into the surface, not a solid surface, but the gaseous sort of atmosphere and surface of that star, isn't gentle. This planet is orbiting around really quickly, and so as it crashes in, some material is both shock heated to high temperatures and kind of thrown out. And then the second thing that happens is that planet, as it falls in, feels a drag force on its surroundings and is kind of torn apart and decays towards the middle. Those ejecta are completely key to the light that we see. So in a supernova, what we're seeing is the blast wave of the envelope of that star that's expanding, and as it expands, eventually light can start to leak out of it, and it causes the brightening that we see. And in the case of a supernova, some of the temperature of that gas comes from heat from radioactive decay. And in this case, there's no extra heat. So the gas just cools off and cools off and cools off. And so as it fades away, it gets cooler and cooler and cooler. So imagine you just took a chunk out of the sun and you sort of threw it outward. As it expanded, it would just cool and cool and cool and get redder and redder. A lot of the work that I do is making gas dynamics models of this sort of process to understand how gas moves as stars are interacting gravitationally, and then what that means for what we see. So here, wiggling in the middle, is a pair of stars, and one of them has sort of enlarged to the point that it's starting to transfer material to the other one. And what's happening is the small one actually is getting material way faster than it can incorporate. And so that gas can't cool and accrete onto that companion star, and instead it's kind of spilling out into the surroundings. And what you might notice as this kind of like garden hose goes around is that not only is it forming these spiral waves, but also the gas in the background isn't kind of escaping to infinity right away. It's being constantly run into by the next layer of material. And so there are all these layers of sort of internal collisions in that flow, and density shells, and that's sort of shaping the surrounding environment here. And then the last thing is, as the pair starts to fall together, you might have seen that I even switched it to a slow motion view at the very end, but this is a process that they start out sort of separated and you have a thin stream of material. But if you look closely over time, kind of the density of that surrounding material builds up and the rate of decay of the pair speed up. So, and those things are coupled. So the orbit falls in faster and there's more and more material spewed out into the surroundings. So here we switch to a slow motion because at a certain point they start to fall together incredibly quickly. And something we measured from those models is I ran them with all sorts of different parameters, and what I learned is that the mass that ends up thrown out to the environment of the pair is just proportional to the mass of the small thing that merged. And this was one of those things that in hindsight made sense because it's a question of sort of how much energy or angular momentum do you need to get rid of to stop this object orbiting and sort of send it inside the bigger star. It's just linearly proportional to the mass of the second star. And so I made in these models a measurement of how much mass was ejected as a function of the ratio of the two masses. So small objects ejected less mass, big ones ejected more. And in the context of this planet falling in, what we then think is happening is that, and this is obviously not something that we saw, it's just an animation. So what we think is happening is that during that sort of slowly skimming phase, the planet goes around the atmosphere of the star a lot of times. But along the way, it's running into that atmosphere and it's heating up some material and it's throwing it out. But as it expands, it doesn't have any extra heat source. There's no radioactive nickel in that material. And so it just cools off. And as it cools off, eventually it forms molecules of dust. And that changes the apparent colors of the central source and absorbs and re-radiates some of the stellar light in the infrared. And so that drives some of the bright infrared signature that we see. And then you saw at the end of this video, the star kind of like puffs up and becomes bluer. And so the idea is that if you imagine a satellite that's in our own atmosphere and it's skimming through the atmosphere, but it feels a drag force from the air that it's running into. What happens when it gets slowed down a little bit is it falls a little bit further into Earth's atmosphere. And as it falls deeper, it encounters denser air. And so then it's dragged even faster, and then it falls deeper, and then it falls deeper, and eventually it crashes into the Pacific Ocean somewhere. In the case of this star, as the planet falls in, it's sort of pumping heat into that star, and it starts to puff it up and make it more luminous. So in terms of this light curve, we think the fact that this source brightened in the infrared well before the optical peak is that kind of skimming along the surface. And then it just continues to get brighter in the infrared, even as the visible light fades away. And so maybe this fading away corresponds to that sort of a plunge of the planet deep into the star and the eventual kind of settling back to normal. Yeah.
Since the infrared measurements are once every 6 months, could the peak be actually coincident with the visual peak?
Yeah, that's a great question. I think it could be, but something that's interesting is that we don't really. Yeah, so could it be, for example, that there's a point, up there? I think that's completely possible, and that's kind of the folly of putting these little dashed lines between the points where we don't have data. But I think something that's interesting here, and what actually triggered us to look at this object in more detail, is that at least at face value, it seems like the infrared data and the visible data are kind of disjoint. So in a young star outburst or something, they'll just track each other completely. And that's kind of saying that the source is changing in luminosity, but not really in color. And so here, because the relative brightness of the visible to infrared is changing a lot, we're seeing big changes in color in this source. So even if there were a point that's brighter there, it's sort of brightening and fading at different rates in these two bands. And that actually is not super common in a lot of these sources. Okay, this is a simulation, a gas dynamic simulation of a planet, skimming around the surface of a star. And this is with smooth particle hydrodynamics. And so you're seeing the planet is starting to get a little disturbed. So now we're switching to a slice through the star, and you'll actually watch it fall in. Something that's kind of amazing to me is once it's kind of within the star, only makes something like 2/3 of an orbit or 3/4 of an orbit before it's completely disintegrated. And what's happening is that as it's running into stellar material, very quickly it sort of accumulates a column similar to its own mass that is crashed into, and it just kind of stops. And kind of froze on the screen. Let's check. It just kind of stops, and then it falls in, and it gets kind of torn apart by that drag force, that aerodynamic drag that it's encountering. So here's this object. You can watch it kind of just fall in, but also disintegrate along the way. And so since the planet has disintegrated, the star is kind of left, and it has some planetary material sort of stirred in, and it's maybe a little mixed up, and it's got some extra heat. But it starts to kind of fade away. And what you see eventually in both the infrared and the visible bands is that they're both kind of tracking downward. And so we think that this is probably the beginning of the star going back to normal. And I think one of the most exciting things is to think about what is kind of the long-term trend here, and what will this thing look like in 2 years, in 5 years, is 10 years, and can we use that to start to try to connect the dots to other stars that might show some of the signatures of having engulfed a planet in the past? Like, we could try to ask what those signatures are and then identify those kind of before and after sources. So the exoplanet catalog, as we know it, is clearly the before, as is our own solar system. There's lots of giant stars. They must be the after. But we don't actually know exactly what to look for to connect those dots. And the hope is that a source, this source or a source like this source, could be some of the pathway to that. So I'll just close here. Something really fun was that this was on the cover of Nature a couple of weeks ago. I was really excited because a lot of the journal articles we write are, like the Astrophysical Journal is no longer a print journal. It's used to be sort of in rows and rows and rows in the library, in the Woolbach Library, but now it's just PDFs online. And so I was really excited that this was in print, and I was trying desperately to find a magazine stand that had it. So there isn't a magazine stand down in Harvard Square anymore. I went to the Harvard bookstore, I went to the MIT bookstore, I went all over. Nobody, there aren't as many magazine stands as there used to be. And none of them, this is pretty niche, I guess, but none of them had Nature. But nonetheless, eventually I ordered through their website a few of them. So it's kind of fun to have the physical incarnation of something you picked.
I have it in my classroom.
Oh, that's great. I'm delighted. Wonderful. So that's all I have to say. Yeah, but I'd be delighted to answer your questions. Thanks.
I have a quick question.
Yeah.
Can we go back to the green-red graph?
Yeah.
So normally, so I watched that video just the other day.
Yeah.
This star, I can't remember if it was on Sky and Telescope or ATMoB, it was someplace.
Mm-hmm.
And I looked at how the star got brighter and bluer.
Yes.
So we think of stars being a certain color based on their mass.
Yes.
So that's the normal stuff. Right?
Yes.
So where this green curve shoots up,
Yeah.
that's where the planet is actually then absorbed into the star.
Yes.
Thus adding thermal energy to the outer layers of the star. And that's what causes it to increase in luminosity and color, right?
Yeah.
It's not the whole star, it's just the outer part of the star.
Yeah, it's like the outer skin has a bunch of extra heat dumped in. And what's kind of amazing to me is you can ask, say another star fell into the sun. That would be a big deal, right?
Sure.
A grain of sand, that would be like nothing, right? But there must be a trade-off somewhere in between, and that trade-off is somewhere around planet size. But it turns out, and the way you can ask that question is, what is the power that something falling in would deposit, and compare that to the power that's already sort of coming out of the star. And so it turns out that, like, as the sun swallows mercury, the power will be a tiny, tiny fraction of the sun's output at that point. And so you probably wouldn't see anything at all. And the same thing for Venus, the same thing for Earth. And so it's only that we're in this situation where the orbit of the planet was just, a day or two around the star, so it was extremely close, and we think it was a relatively massive planet, something like Jupiter. So a big planet close in could deposit enough heat to actually cause it to visibly brighten.
Sure.
I think like a smaller, say a rocky planet in a giant star would happen too slow and have too little energy to ever cause that change in the stellar color, because you just wouldn't be putting in enough thermal energy.
Mhm.
Yeah.
Yeah, when you think of a planet compared to a star like the sun, you think it's so tiny.
Right.
What's it gonna do?
Right.
But now that decay on the green curve, that's the star returning back to its normal state?
Yes.
Yeah,
Yeah.
that's cool.
That's really cool.
That's cool.
I don't know who wants to go next. Maybe.
So in terms of what happens when the planet goes into the star, in addition to going into the atmosphere of the star itself, is there also a shell around the star? Material, and part of the question is, if that's true, you have to adjust that green light curve for extinction of the shell.
I think so. And so something that we see is, and I think that's a really insightful point, but I think basically something that we see is that there's more and more material piling up around the star. So there's more and more circumstellar material. That's changing the colors of the source. And so it's the fact that it's more infrared luminous relative to visible tells you right away that essentially the extinction from the star has increased. So there's more dust around. And we use that actually to estimate the dust mass in the system. But yeah, that's a really good point. So we have in October, JWST observed this star. And we've been working on analyzing those data. And something that they show that is kind of puzzling at first is they show both quite cool dust, so a few hundred Kelvin. They show warm dust, so like 1,000 Kelvin. And they show actually molecular emissions, so carbon monoxide rotational transitions. So that's at a few thousand Kelvin. And the stellar surface is maybe 4,500 Kelvin. And so basically it seems like you have gas and dust around this star, both very close and hot, thousands of degrees, kind of medium, 1,000 degrees further away probably, and further out and colder, only hundreds of degrees. And so I think you're right that kind of like spewing out of material does form a shell around the star. But in this case, it seems to be that not all of it is just thrown out in one go. It's like there's some of it still kind of hanging around in kind of probably some.
Well, you showed before, earlier you were showing those orbits. The spiraling, so you'd have.
So that's kind of my qualitative picture is that, yeah, there's many orbits and stuff is kind of piling up in the surroundings, and you maybe have sort of hotter gas closer to the star, and some material is escaping and powering this emission that we see, but there's some still left kind of bound. And eventually that will cool off and reincorporate into the star, but it probably takes quite a long time for that to happen.
Do you think that dust that's being expelled is in when I think of shell, I think a sphere.
Perfect sphere, yeah.
Or do you think it's more of like a?
I think it's more equatorial.
Because then the extinction fact would be, this kind of thing.
Yeah. I think it probably depends quite a bit on what angle you look at.
Yeah.
And we don't know what angle we're looking at.
Right.
So that's the trouble.
To find a bunch of.
Yes. Yeah.
Now, these stars, they're obviously going red, so they're not fusing hydrogen anymore, or are they still fusing hydrogen?
They are, but not at their very core, just in a shell.
Okay,
actually.
but does the introduction of all these heavy elements from the rocky planets they're consuming, how does that interrupt the process?
I think there's a couple interesting questions. So one is, does the planet kind of like stir up the star enough. And so you take everything you have and maybe you stir it up, you add a rotation. Maybe that helps mix kind of fresh material from the envelope down towards the burning layers. Short answer is we don't know. The other thing that could happen is that you add heavy elements and those actually change kind of the observed spectra of those stars, because when we look at absorption lines in a stellar spectrum, we're seeing the heavy elements against the kind of continuum of thermal emission. And the sun obviously has a lot of heavy elements. We see iron lines, we see sodium lines, we see calcium. But there are some elements, and in particular, lithium is a very fragile element. It tends to be destroyed rather than created in stars. But in planets, it survives. And so Jupiter has sort of much more lithium than the sun does. And so one question is, if you add a planet worth of rocky material, do you enhance elements like lithium that are destroyed by the burning processes in the star? That's been at least sort of contemplated as one potential signature of sort of an event like this having happened in a giant star's past. And so we're really hoping that we can like look at this in as the dust clears, so to speak, and try to take a spectrum like that and ask whether you see the sort of chemistry of the planet as opposed to the sun. Yeah. All right.
5 or 6 years ago, I did data collection for 2 years with one of your predecessors here on WD1145.
Okay.
And a white dwarf.
Yeah.
That also ate its. But when we modeled that, I didn't model it.
Yeah.
When CFA modeled it, they said that it hit a Roche limit and disintegrated, and its stuff kind of just laid down on the surface. So why does this planet survive and not fall apart?
Yeah. Okay. So in that white dwarf system, just for everyone, what people think happened is you had some rocky thing, like an asteroid maybe, and it's orbiting around this compact white dwarf star, and at some point, the gravity of the white dwarf sort of splits it up, and it fragments, and all the little bits fall onto the surface. And then what you end up with is the chemistry of that asteroid sort of polluting the surface of the white dwarf. And so a really analogous thing might happen here. What we think might be different is that in this case, the planet is going inside the star versus the star going inside the planet. And, or not that last part, but the planet, sorry, we're passing. So you may or may not realize that I'm only a sort of somewhat real astronomer in that I do mostly computer simulations because I'm extremely bad at staying up all night. And I realized that sometime around, like when I was in college, and I figured if I couldn't stay up all night then it was only gonna get worse. Okay, so the other thing that can happen is that the gravity of the star can rip apart the planet or the asteroid. And what really determines that is the relative densities of the two. So if the planet is denser than the star, it can go inside. If the planet is less dense than the star, the tides of the star will rip it apart before it could ever enter in.
Is it that the star was already a giant and the Roche limit is closer to inside the star as opposed to outside the shell?
Yes.
Okay.
Yeah. Exactly. Yeah.
Are there any changes that happen when comets hit the sun, which happens often?
Yeah, I think that would fall into the category of like being too small for the sun to even notice. Yeah. And so, I mean, that object is disintegrating. If you looked closely enough, you could see like its pollutants on the surface of the sun for that sort of brief moment, but it wouldn't change the sort of baseline power output that's coming out of the sun.
Does it change the spectrum at all?
I mean, it might change the spectrum of that patch on the sun. Yeah. I don't know. I don't know of observations of that, for example. Yeah.
when you just talked about the size of the objects, made me think about Shoemaker-Levy 9.
Yeah.
Was there any way to correlate what we saw there to what you're seeing here?
Well, that's a really
It's
beautiful
kind of
point.
almost like just a scaled down model of what you're
I think it is because, you know, in a lot of ways you have basically like the smaller object running into the bigger one. Something that we were really struck by when, not with this object, but with the stellar merger transients that look really similar, is these really steep rises. So how do you take a system that's existed for millions or billions of years, and all of a sudden in, you know, just a few orbits, it all goes wrong, and you end up with this really dramatic rise. And for a long time, I thought that these must be collisions, more like the Shoemaker-Levy, the collision with Jupiter. And what kind of defines that is that rather than the comet orbiting around the planet for a long time, it's just sort of a one-off like crash. You can imagine a one-off crash is a great way to make that really fast rise in brightness and then the fade away. But what it doesn't do for you is that slow kind of percolating rise. And so that's where they're a little bit different.
Yeah.
But I think that's a really beautiful point about thinking about sort of the like impression that those collisions left in Jupiter's sort of cloud surface and like how long that lasted. I think there might be some lessons. Yeah, that's really interesting. Well, it's been such a pleasure to talk about this with you all, and it's fun to be here.
Thank you, Morgan.
Yeah, it was fantastic. My pleasure.
So with that, I can officially close the meeting. I just want to remind people that we did vote to hold the July meeting, which will be July 13th. So that'll be our next meeting. And we do have a board meeting coming up on the 22nd, which is sort of the big annual budget meeting. So if you have ideas for projects, run them by us and we can discuss it during that meeting. Thank you all.
Thank you.